Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe characteristics of estimators. Sampling distributions allow us to evaluate the performance of estimators, such as the mean. Three important characteristics of estimators are that they are unbiased, efficient, and consistent. The estimate we get when we use a sample mean to estimate a population mean is unbiased and consistent. It can be efficient under the right conditions. When you compute other statistics to estimate population parameters, for example, a standard deviation, the estimate might not have all three of these characteristics. The first characteristic is being an unbiased estimator. This is a statistic with a mean value over an infinite number of random samples that is equal to the parameter that it estimates. The sample mean, x bar, is an unbiased estimator. What this means is that if we took all possible random samples from a population, or an infinite number of samples, then the mean of the sample means would equal the population mean. In other words, the sample mean shows no systematic tendency to deviate from the population value. With regard to systematic tendency, sometimes the sample means will be higher than the population mean, and sometimes they'll be lower. Now that we've learned about the sampling distribution, we understand that this property says the mean of the theoretical sampling distribution will be equal to the population mean. Let's do a little example. This example isn't perfect because obviously I can't show you taking an infinite number of samples, but it will give you a concept of a mean of the means. If I want to know the mean number of times that 0 to 6-year-old kids watched Peppa Pig last month, and I took all possible random samples of n equals 10, 0 to 6-year-olds from the population, I could compute the mean for each of those distributions. So there's a pool of all of the 0 to 6-year-olds, and that's my population. I select a random 10 kids, and that forms one distribution of scores, or the sample. Now those 10 kids are put back into the pool so they have a chance of getting selected again. This is sampling with replacement. More on that in a minute. Then I select another random 10 kids, and that forms the next distribution of scores or sample. You can see in this chart that this chart contains just 5 distributions composed of 10 kids' scores, but remember there's an infinite number of the distributions. We've talked about this when I introduced sampling distributions. So I compute a mean for each of these samples distribution. The mean of the samples are 9.6, 11.2, 11.4, 10.2, and 11.2. So I can take a mean of those means. If I add those means up and divide by 5, it's 10.72. Now we've seen that example of taking the mean of the statistic computed over, let's say, infinite samples. Let's look at the definition of unbiased again. Remember, an estimator is unbiased when it has a mean value over an infinite number of random samples that is equal to the parameter it estimates. This is saying that the mean of means from the sampling distribution is equal to the population mean. The mean is an unbiased estimator. So if we really had taken an infinite number of samples instead of just 5 samples, that would imply that the population mean, mu, would be equal to 10.72. Another way to think about unbiased is that if you keep taking samples from a population, in the long run, the means will average to be the population mean. The next concept is a consistent estimator. Consistency means that for a given estimator, the probability that the statistic has a value close to the parameter increases as the sample size increases. The sample mean is a consistent estimator, meaning the sample mean has a higher probability of being closer to the actual population value as sample size increases. That is, if we pulled many samples from a population and took the mean of each sample mean would be closer to the actual population mean if each sample size was n equals 1,000 instead of n equals 10. The higher the size of the sample mean, the closer each sample mean is to the actual population mean. This means that the sampling distribution of means would get narrower as the sample size increases. Remember that the standard error of the mean represents the standard deviation of the sampling distribution. This means that the standard error of the mean decreases as sample size increases. Let's look at an example. Here's an example of consistent estimation. We are going to pretend that we only have 20 people in our population just for teaching purposes. These 20 people are in the column on the left. The actual population of whatever or whoever you're studying is likely much larger than 20. So these case numbers just apply to this population distribution for this example. So let's say we have 20 people in our population and we collect data for those 20 people. That's everyone in the population. And we calculate the mean as 8.95. This is our population mean mu. In our example, the population mean is known. We've calculated it. I've also sampled 3 other distributions from the total population here. One of 14 people, one of 7 people, and one of 2 people. A higher proportion of scores from the population are being included in the larger sample. The mean is a consistent estimator, which implies that the larger our sample is, the better our estimate of the population parameter. This is because the more people are in the sample, the closer that sample is to being the size of the actual population, so the computations are closer to exact. You can see that that's the case here. Our mean with 14 people is closer to the population mean than our mean with a sample size of 2. Note that the mean for the sample size of 14 is 9.79 compared to the population mean of 8.95. The sample of size 5 has a mean of 10.20, getting farther away from the population mean. And then the sample of size 2 has a mean of 13, getting even farther away from the population mean. So as sample size decreases, the calculated sample mean moves farther away from the population mean. Finally, let's consider efficiency of an estimator. An estimator can be unbiased and consistent, but it's still an estimate. So if an estimate is efficient, we are asking if it is on target or if it's accurate. And whether or not the estimate is on target or accurate depends on several factors. It depends on sample size, sampling method, and the variability of scores in the population. So let's go through these now. So sample size was just covered when discussing consistent estimators. The larger the sample size, the better the estimate. So for consistent estimators, a larger sample size yields better estimation. If your sample size is large enough to equal the population size, essentially your sample is your population, then you'd have perfect estimation. You could say that X bar is equal to mu. Next is sampling method, and this is how you choose your sample. So we want the sample to be representative of the population. And this means that the characteristics of the sample should be similar to those in the population. So if we want to know about American children, for example, you wouldn't get a sample that includes only boys, only kids from divorced families, only rich kids, or only poor kids. If you want a representative sample of American children, you would want to get a sample that includes boys and girls, kids from divorced families, nuclear families, blended families, etc. You want the sample to have characteristics that are similar to your population. So to obtain a representative sample, we can use random sampling. So random sampling is when each member of the population has an equal chance of being included in the sample. And there are a few different types of sampling methods we can use to ensure that we are randomly sampling. This means that the selection of one member is independent of the selection of any other member of the population. So an example of this, an example of a random sampling method would be if each person in the population was assigned a number, and then the numbers were put into one of those lotto ball machines, which randomly selects numbers. If your number is called, then you are selected for the sample. You're randomly selected. This means that each person has an equal chance of getting into the sample, each person in the population. Now, the picture I've included here is from the Hunger Games movie. If you've read the books or if you've seen the movie, the selection process in the Hunger Games is sort of like random sampling, but it's a little different because they put restrictions on the sampling. In the Hunger Games, they select children to fight in games, and they select 2 children each from 12 districts. Within each district, they only select 1 boy and 1 girl between 12 and 18 years old. So it's similar to random sampling, but this might be considered a form of what's called stratified random sampling. The population of 12 to 18-year-olds is divided into groups, first by district, each of the 12 districts, and then by gender, male or female. And then from each of those groups, a person is randomly selected. Also to note that with a finite sample, random sampling is only possible with replacement. So now we know that sample size and sampling method increase the efficiency of our estimation. Another thing that affects efficiency is variability in population parameters. This essentially says that the more spread out the scores are in the population distribution, the greater the chance of selecting a sample that won't be representative of the population. Another way to think about this is that the larger the population standard deviation of the distribution, the less likely that a particular sample mean will be an efficient estimate of the population mean. So essentially, we want less variability in the population to get an efficient estimate of a population parameter. So think about this. If you've got a distribution that's more like the distribution B in this figure, then the majority of the sample has values close to the mean. You can draw a sample, and most of the sample is going to be similar to one another and close to the mean. However, if you've got a population distribution that's more like A, the blue distribution, the people are more dissimilar from one another. If you draw the sample from A, the people may be close to the mean or farther from the mean. This concludes part 3 on models of error and distributions. In the next lecture, I'll describe the assumptions we make about error.